This presentation is about some of the properties that solutes give to solutions, and these properties are independent of the identity, for the most part, of the solutes involved. So they're dependent on the number of solute particles, not their identity. One thing to note is that the presence of a solute will change the boiling temperature of a solution. For just pure water, the boiling point is 100 degrees Celsius, and the actual physical definition of what the boiling point is the point where the vapor pressure of the liquid, in other words, the pressure exerted by the liquid particles escaping into the gas phase, is equal to the atmospheric pressure. That's why the boiling point is different at different elevations. For instance, if you look at some things like pasta or mac and cheese, you'll notice that they have high altitude cooking instructions where it takes longer to cook the pasta. And the reason is that the water boils at a much lower temperature up in Denver than it does down here in central Iowa. So because the boiling point is lower, it's going to take longer for the pasta to cook. So, like I said, the vapor pressure is equal to the atmospheric pressure when we're at the boiling point. And the normal, sometimes we use the term normal boiling point, and the normal boiling point is when the vapor pressure of the liquid is exactly 1 atmosphere. Okay, so I've got a left-hand beaker here, which is just pure solvent, probably water in this case. And it's at the boiling point, and I know this because the two arrows for the atmospheric pressure and the vapor pressure are equal to one another. So the vapor is pushing up with exactly the same force that the atmosphere is pushing down, and I'm at the boiling point. Now, if I add a solute to this, the vapor pressure of the solution decreases. There are a variety of ways of explaining this. Most textbooks on our level use kind of a simplistic view of that the particles block the escape of some of the liquid from the liquid phase into the vapor phase. So because I've got solute particles in the way, and if water molecules are trying to escape, they can bump into those particles and get ricocheted back into solution. And if that's happening, the vapor pressure is lower. Sometimes they also kind of point at the increase in the amount of attractions. The water particles are attracted to these solute particles, and therefore it's harder for them to break free and escape into the vapor phase. So either way, that tends to work without invoking deep thermodynamic thoughts in terms of what's going on here. So if the vapor pressure is lower in the presence of the solute, in order to bring that solution to a boil, I've got to add more heat to it. In other words, bring the temperature of that solution up to increase the vapor pressure. And the extent of this for water is about a ½ degree Celsius per molal. And molality is like molarity, but rather than being moles per liter of solution, it's moles per kilogram of solvent. So roughly the same for relatively dilute solutions. So for every mole of solute that I add to a liter of solution, the boiling point only increases by about a ½ degree Celsius. I know that one of my pet peeves is when I'm watching cooking shows and they grab a pinch of salt and they throw it into the pasta water and say something like, that's to increase the boiling point or make the pasta cook faster. And it couldn't be farther from the truth. The amount of salt that they added barely raised the boiling temperature. The only reason we add salt to pasta water is because, well, one of our flavor receptors is salt, so we have an affinity for salt. Okay, freezing point is a little bit more involved in terms of the explanation. The actual definition isn't really that big of a deal. But the freezing point is physically where the vapor pressure of the liquid and the solid are in equilibrium with one another. And I've kind of displayed this in my left-hand beaker where I've got this at the freezing point where I've got the solid and liquid in equilibrium. I've got that white ice cube that's in there. Its vapor pressure is the same as the vapor pressure of the water. Now, in the presence of a solute, again, if we either use attractions or just blocking the surface, the vapor pressure of the liquid is going to decrease. And in order for this to actually reach the freezing point, we're going to have to go to a lower temperature, and the extent to which the vapor pressure decreases for a solid is greater than it is for a liquid. And eventually, as we lower the temperature, they're going to reach an equivalence point again, and that will be our new freezing point. For water, this is almost 2 degrees Celsius per mole per kilogram. So if I spread a mole of a solute onto a kilogram of water, and a kilogram of water would spread out quite nicely, might cover several square meters spread thinly, just like if you have ice on your driveway. So adding a solute to that is going to cause the freezing point to decrease. So it's not going to be freezing right at 0 degrees Celsius, it's going to be a couple degrees below. And if you add enough salt, you can keep the water from freezing down to quite a few degrees below 0 Celsius. Osmotic pressure is another phenomenon that's related to solute particles, and I've got a couple of beakers to illustrate this. Generally what we have is what's called a semi-permeable membrane separating 2 compartments, and on one side I have just pure solvent, and on the other I have solvent plus solute. And what happens here is the water molecules are small enough to pass back and forth, but the solute particles are too big to get through these tiny pores. And the net effect is that there's more flow of water into the compartment with the solute than there is in the reverse direction. So what happens is what we end up with on the right, where because there's more solute flowing in than out, the water in one compartment rises in that compartment and actually decreases in the other. And you've probably seen this if you have a biology class. I know what we did is we took, back in the day when we used to poke ourselves in the finger in lab, we would squirt a drop of blood onto a microscope slide, and actually do it on 3 microscope slides, and we would add hypertonic, hypotonic, and isotonic solutions to those drops of blood. The ones that were isotonic, nothing happened to the red blood cells. They were just perfectly happy and fine. If I added something that was hypotonic, that means less solute on the outside of the red blood cell, then the water would rush into the red blood cell and it would explode, leaving behind kind of a ghost-like shell of a red blood cell. And then if we put it into a hypertonic solution, the red blood cell just kind of shriveled up, or I think the fancy word is that it was crenated. So the red blood cell ends up all crinkly looking, kind of funny looking. And that's kind of an example of osmotic pressure in action. Now, in terms of solutes, all solutes aren't created equal. Solutes that contain ions will separate into their ions, so you get more bang for your buck. So if I add 1 mole of sodium chloride to a solution, it's going to fall apart into sodium and chloride ions separately. So 1 mole of sodium chloride provides 2 moles of solute particles. Calcium chloride provides 3 moles of solute particles because it contains 1 calcium ion and 2 chloride ions, and then the rest are all twofers here. Potassium nitrate, 1 mole of that gives me 2 moles of ions. Sodium hydroxide would fall apart into 2 moles of ions, and even an acid like hydrochloric acid ionizes fairly completely, and we would end up with 2 moles of ions. Covalent compounds, on the other hand, do not ionize in aqueous solutions, so things like glucose, or I picked insulin here, or iodine. If you notice, these are all nonmetals in the formulas. So if they're all nonmetals, they're not ionic. They don't separate into ions, no matter how many atoms are involved. You only get 1 mole for 1 mole of any of these as solute particles. So if I add 1 mole of glucose to water, I only get 1 mole of solute. If I added 1 mole of sodium chloride, I get 2 moles of solute. So let's take a look at this. I want to know how many moles of solute particles I have in each of the following. So I've got 0.237 moles of sucrose, so that's my starting point. And I know that I get 1 mole of solute for every 1 mole of sucrose, so the effective concentration remains the same. Calcium chloride is a little different. Like we saw in the previous slide, it breaks apart into 3 ions. So if I know that I get 3 moles of solute for every 1 mole of calcium chloride, I multiply by my concentration, and my effective concentration of solute would be 4.35 moles per liter. Potassium phosphate is way out on the other end here. If I look at that, the 3 potassium ions separate from the 1 phosphate ion, and I get 4 moles of solute particles for every 1 mole of potassium phosphate, and I get a multiplying effect of 4 here. So it's going to be in the neighborhood of 0.468 moles per liter of solute particles when I'm dealing with potassium phosphate.